Hi, my name is Chun-Jen Tsai, and I'm with the Department of Computer Science at National Jiaotong University in Taiwan. Today, I'm to talk about an open source image pyramid accelerator for embedded processors. This accelerator is designed for FPGA devices. This is the outline of my talk. First, I'll give an introduction about the applications for image pyramids. Then I will discuss some related work on image pyramid accelerator design for FPGA devices. And then I will show you the proposed architecture. And then we will present some experimental results. Finally, I'll give you some conclusions and future work. An image pyramid is a sequence of downscaled images. You begin with an high-resolution original image, and then you keep scaling down this image to create a sequence of lower-resolution images. It has a very interesting feature that if you put a fixed-size analysis window at different layers of the image pyramid, for high-resolution layer, you see more details in a local area, while for lower-resolution area, you see more global information. So this property is very useful for computer vision applications or image analysis in general. Image pyramid is also good for space-time trade-off. Like for example, if you have a low frame rate video sequence, 2 consecutive frames in the video sequence may have long temporal distance, which makes motion analysis quite difficult because when the temporal differences between 2 consecutive frames is large, the motion can be hard to predict from frame to frame. However, if you generate image pyramids for each of the video frame, scenes will be much different because for motion analysis, you can first try to perform the analysis on 2 consecutive frames with the lowest resolution, and effectively the temporal distance between low-resolution images will become much smaller because when you scale down the image spatially, in some sense, you also scale down the temporal distance between 2 consecutive frames. So the motion becomes smaller, and then it will be easier to predict the motion from one frame to the other. In this slide, we show you a list of previous work on image downscalers for FPGAs. As you can see, most other downscalers are based on simple Gaussian or bicubic filters with very short tap lengths, while in our case, we use the Sine-windowed Sinc function filter with a long tap length, and that's why we can produce the best scaling quality. And also we support up to 24 different scaling factors, while many other designs only support fixed scaling factors. And even some of the design allows for parameterizable scaling factors. They are limited to a smaller number than 24 levels. In this slide, we show you some design decisions for the proposed image downscalers, including the hardware-software partition decision, downscaling factor decision, and memory architecture decision. In this slide, we show you the timing diagram of the filter process. First, we perform horizontal scaling. Right. And before you do scaling, you have to read data from the DRAM, the main memory, right? And once we stored enough pixel data in the DRAM, the horizontal scaling process will begin, right? So after this point, the reading of pixel data from the DRAM and the scaling operation inside the image scaler will be executed concurrently, right? And the output from the scaling result will be returned to the on-chip memory. That's the intermediate pixel result, right? Because we have to store it in on-chip memory for another round of filtering operation, right? So once we finish the horizontal scaling and the storage of the horizontal scaling result on the on-chip memory, we will begin the vertical scaling process. So this process will read the pixel data from the on-chip memory and then perform scaling operation. So as soon as one row of data is done, we will write the data to DRAM, right, until we're done with the execution. It is possible to overlap the horizontal scaling process and the vertical scaling process to a certain degree if the memory bandwidth is not limited. But since for the verification platform we use, the FPGA development board we have some constraint on the DRAM bandwidth. So it does not make sense for us to try to overlap the horizontal scaling process and the vertical scaling process, because that will make the control logic quite complicated, and it doesn't really give us much advantages, because most of the time we'll just be waiting for data to coming from the DRAM and to be written out to DRAM, right? So memory bandwidth constraint, memory bandwidth is the current bottleneck in the proposed system. For this work, we have used the Xilinx EDA tool, Vivado 2018.2 to develop our system, and the development board, the FPGA board we use will be Xilinx KC-705. And you can go to our GitHub website and download the entire a sample workspace that contains the entire hardware and software for the proposed system. And then once you open the sample project workspace, you have the hardware design window, IDE window, and then you have the SDK window for software design. And you can synthesize the bit file for FPGA programming, and then you can configure the FPGA with the hardware and try to run the software from the Vivado SDK. Once you execute the software, you will see some prompt in a Teraterm terminal or any terminal emulator you want. You will see some prompt ask you to send an image file to the development board through the serial cable for processing. So for Teraterm, you can go to the file menu and then select send file, and then a browser will pop up for you to select the image file you want to transmit to KC-705 for image scaling operation. And your image file has to be a PPM file, because that's the only image format we support so far. There's a sample image on the GitHub website, so you can use that for a starter. Anyway, once the image has been transmitted to the FPGA board through the serial cable, the FPGA board will scale it and then convert the scaled pixel using software. Convert the scaled pixel to some text printout on the terminal window. So you have to actually turn on the login capability inside your terminal emulator. So these output will be stored into a text file, a log file in particular. And we have provide some tool, scripting tool on the GitHub website, so that the tool will read in the log file, and then we will parse the log file, extract the output image from the log file, and then save the output image into another PPM file. So you can use any image viewer that supports PPM file to open it up to see if the scaled image is correct. And so that's the setup for our experiment. Okay, in this slide, we show you the usage of logic resources on FPGA, on a Kintex-7 FPGAs of the proposed system. The downscaler accelerator itself is quite small. Right? It didn't use much resource except for the block RAM. It used a lot of block RAM, 128 blocks of 4K byte block RAMs. And these block RAMs are mainly used for storage of intermediate scaled pixel data. Right? A breakdown table of how we use each part of the block RAM can be found in the paper. So if you're interested, you can look into that table. And the usage on block RAM can be reduced if you use other more complicated control logic, so that only part of the intermediate result will be stored inside block RAM. That's possible. Yeah, but nowadays block RAM is not really an expensive resource, so there's really no good reason to do that. Besides, the target application for our scalar circuit or image pyramid generator is for computer vision applications, especially for intelligent image analysis. Right? So nowadays, like most people use artificial neural network for that purposes. So the artificial neural network itself has some constraint on the input image size, and typically nowadays many popular image recognition algorithms will scale down the input image to the size of around 512 by 512 before you feed that image into the artificial neural network. So from the beginning, our design has been targeted for a top resolution of 460 by 480, 640 by 480. Right? For that kind of resolution, storing all the intermediate result is not a serious problem. Right? The full system itself actually occupies 13% of the lookup table on the FPGA, which is kind of big because the capacity of the FPGA we use is quite large, and most of the circuit resources are used by the memory controller. Actually, the memory controller is a standard IP provided by Xilinx, and also part of the logic resource has been used by the microblade RISC processors, the cache system, and the AXI4 bus infrastructure logic. Okay, but overall, this design, the proposed design, can fit into a smaller size FPGA. Okay. Here we show you the clock cycle it takes to scale the original input image of 640 by 480 down to various resolution scale. And so we show you how many clock cycles it takes to do horizontal scaling for different resolution, and to do vertical scaling for different resolution, and then finally the overall time to scale the original image to different resolution. And these numbers are measured in real time using a hardware clock counter, tick counter, so it's quite accurate. And so it's a number from a real system with image data stored in DRAM, reading, scaled, and then output to DRAM. Right. So the number is not from simulation. And so based on this table, on this chart, we know that our current implementation on the particular FPGA board can generate 11 pyramids per second, 24 level pyramids per second. And the main constraint comes from the memory bandwidth, because right now our design uses 32-bit DDR3 memory running at a memory clock of 200 MHz. And in fact, this FPGA board has an option of using a much wider memory bus, right? So if we increase the memory bus by like 3 times at the same clock rate, then we would be able to produce more than 30 pyramids per second in real time. Finally, some conclusions. In this paper, we have presented an open source 25 level image pyramid accelerator for general purpose application processor. And in this image pyramid generator, the downscaler design is based on a sophisticated SWS long tap filter. So it produces pretty good scaled image quality, and that's intended for computer vision applications. And this system should be able to generate 30 pyramids per second, and each pyramid has 24 levels. As long as the DDR3, the memory bus, can handle like 128-bit at 200 MHz or 32-bit at 800 MHz. Right. In our current implementation, the memory bus we use has 32 bits at 200 MHz. So we cannot really generate 30 pyramids per second yet. However, in the future, we will modify the memory subsystem so that we can handle real-time generation of 25 level pyramids. Finally, computer vision applications typically use an image pyramid for image analysis, right? So in particular, we will look into an application that computes optical flow from a sequence of image using a coarse-to-fine approach. So far, a coarse-to-fine approach based on the optical flow equation is considered to be the best, one of the best techniques for motion analysis for an image sequence. So in the future, we will design a complete system that adopts this proposed image pyramid generator for optical flow estimation applications. And that will be the end of my presentation. Thank you for listening.